Hi everyone, this is Worksheet 4.1, the free particle. And this is our opportunity to talk about an unusual system in this class because this system is not a standing wave. A free particle is free to move anywhere in space, and so therefore its wave will be moving around with time. And the result of that is that it will not adopt bound states, but will adopt scattering states. And we will see that it also has no definite energy. The energy is actually uncertain, and that prevents it from appearing in discrete energy levels. So let's begin by writing down the Schrodinger equation as we know it. H bar squared over 2m, second derivative of the wave function with respect to x, plus let's say that the wave function is a function of x, plus the potential energy function times the wave function equals a constant E times the wave function. All right, the potential for a free particle is constant everywhere. And this is in contrast to the particle in a box, because in a particle in a box, it's not constant everywhere. There is a domain in which the potential energy is constant, but then outside of that domain it's infinite. And it turns out that we can describe this system exactly by assuming that the potential is just zero everywhere. It turns out to be the same dynamics whether it's a non-zero constant or whether it just equals zero everywhere. So that means that we can write the Schrodinger equation with that v of x function just equaling 0. So the second derivative with respect to x just equals e psi, like that. Now we need to multiply both sides by the reciprocal of this expression over here. And what we get is that the negative second derivative with respect to x just equals 2me over h bar squared psi. And we can define this value k as the square root of that expression that's there right next to the wave function. It's the same k that we had for the particle in a box. We can call this quantity the wave number for reasons that we'll explore later. And we can rewrite our Schrodinger equation as the second derivative of psi with respect to x squared as being equal to negative k squared psi. Now, this is a differential equation, and we saw one of the solutions to it in the particle in a box problem, but for a free particle, it's going to make more sense for us to define the solutions as follows. The first solution, which I'll call psi positive as a function of x, is going to be some normalization constant a sub x, which is just to indicate that this is a positive wave function, which will become clear what I mean by that in just a second, e to the I k x. And then the other solution I'm going to call psi negative as a function of x. And there's going to be a normalization constant subscript negative I kx. So both of these are solutions to this differential equation right here. Now, the next step will be to tack on the time component. Because these are going to be time-dependent waves, so it makes sense that we'll want to put the time component back on. And remember that the time component is e to the negative I e t over h bar. But using my definition that relates e to k right up here, I can rewrite this algebraically as e to the negative I h bar k squared t over 2m. And you can pause the video right now if you want to and verify that algebraically if you're interested. So now let me define my time-dependent wave function positive. It's a function of x and t. It's going to be this normalization constant here, e to the I kx times e to the negative I h bar k squared t over 2m. And I can combine what's above these two exponents into a single exponent, and this becomes a plus e to the power of I k x minus h bar k over 2m times t. So that's kind of interesting. Let's write now the negative one before I explain what the interpretation of that expression is. So I get that negative normalization constant now, and I do the same thing as I did here, just adding what's above the exponent, and I get e to the negative I k x plus h bar k over 2m t, like that. Okay, I would like to point out something interesting, that these two functions here are functions of x plus or minus a variable I'm going to call v times t, where v is actually equal to h bar k over 2m. And it's no accident that I chose v, because v is actually a velocity. So this variable right here describes some sort of velocity, and it turns out to be the velocity of a wave. And what it looks like is, if I plot this psi plus, what it looks like is a wave like this that is maintaining a constant profile and moving in a positive direction. So I'm sort of drawing this wave further back in time here. Not very well. Something like that. So the wave is moving in this direction. It is a wave of fixed profile, moving forward or backward in space and time. Okay? Let's see what this psi negative looks like. It is the exact opposite. So now, if it has a wave profile like this, then in the past it looked something like this. And it's moving in this direction, like that, at a constant velocity. And over here, hopefully you're convinced that the shape doesn't change as it propagates, because it's just a function of the position plus or minus the velocity times the time. And that's the type of wave that these functions are describing. Unfortunately, waves like this in quantum mechanics actually do not exist. We went to all that work to show you what a wave like that is like. But the problem is that those wave functions, plus or minus, cannot actually be normalized. Why not? Well, remember that this is a free particle, so it's actually over all space. So let's try to normalize those functions by integrating over all space. So we've got our psi. Let's just do psi plus for now. And we find its absolute value squared integrated over all of space. And I can, by the way, this all depends on the assumption that I can separate the time and space component. So we saw earlier in the class that if you can do that, then you can just write the space-dependent eigenfunction there, integrated over space. And this is just the complex conjugate of the eigenfunction times the eigenfunction dx. And this becomes, let's write out those wave functions explicitly, those eigenfunctions explicitly. A plus e to the negative ikx, because of the complex conjugate, I'm changing the sign of the I, ikx. Hopefully you recognize that these two things add together, and this whole expression here just becomes 1. And that's not good, because that means that we've got, I forgot my squared up there, we've got a plus squared integrated over all of space, and hopefully you see that this is impossible, because when I integrate that I get a squared infinity minus negative infinity, and this whole thing right here ends up to be something like 2 infinity, and that's not going to work. There's no way that you can make that equal 1 and actually normalize this function. Therefore, the result of that is that these states, that is a wave that maintains a fixed profile as it moves, cannot be physically realizable. And I didn't go very deeply into this, but the conclusion from this analysis is that there is no such thing as a free particle with definite energy. Because if it has definite energy, that implies that the wave profile remains fixed, and it can't do that, so therefore scattering states, continuous energy levels have uncertain energy, and there is no definite energy. The energy is uncertain.